This is Cosmos DB for SQL Server professionals. How many of you have actually fired up a Cosmos DB instance and started tinkering with it? Cool, excellent, that's great. So a little bit of housekeeping. Please silence cell phones, just like we said yesterday. I don't really care, but we'll probably make fun of you if the phone rings and you've got a weird ringtone. So keep that in mind. If you've not already explored a lot of the other things that PASS has to offer, it's really great content. There's just an incredible stream of content all the time, a lot of blog posts, a lot of videos, a lot of virtual chapters, local user groups, all kinds of really good stuff. So if you're here, you probably know about it, but really dive into a lot of the other content. It's all year round. It's fantastic. Session evals. These really do matter. Not just for you to just say, yeah, you suck, and that's about it. But realistically, it matters for us. We want to become better speakers. It helps them figure out what content to present next year and to select. It does matter. So be constructive. If the room is cold, sorry, we can't do much about that from up here. But if there's content or critiques, we do want to hear it. So be honest. So bottom line, my name is David Klee. I'm the founder of Heraflux Technologies. You can kind of call me the geek in the room, except for this guy, he's a bigger geek. I'm a Microsoft Data Platform MVP and a VMware vExpert. I have a lot of fun playing with big toys all the time. I lead a consulting company where we travel around and play with how big infrastructure and cloud deal with very large and highly advanced SQL Server workloads. It's kind of fun.
And my name is Bob Pusateri. I am a solutions architect at Heraflux Technologies. I'm not sure if I'm a bigger geek or not, but I am a Microsoft certified master, which means I was a fairly big geek a couple years ago at least. So that works.
Cool. Okay. Yesterday, Bob and I talked a lot about the theory of Cosmos DB. So we're going to go through an abridged version of that, but we're going to make this more hands-on, more real world. If you want to go back and watch more of the theory, they've got the recordings that they'll have those released pretty soon. Go back and check those out. But now we're going to switch gears. So how many of you go collect performance metrics and telemetry across your environment today? Should be everybody in the room. Let's do this again. How many of you collect all of this? Thank you. So raw Windows perfmon information is what we're going to focus on right now, and that includes system state. You can include a tremendous amount of SQL Server counters, all kinds of good things. So we're going to keep going back to this theme. So if you look at a payload of perfmon information, first of all, you have the group. So it could be processor, network, physical disk, things like that, things that actually, kind of the overarching set of information. In each one of those, then you have the counter. So let's say percent processor time or average disk seconds per read or per write. And then there you have the instance. So if we're talking about CPU-related things, you've got, let's say, CPU 0, 1, 2. If you're talking disk, it could be C drive, E drive, L drive, whatever it is. Inside the instance, now you get a value, and you have a collection date and time. Basic hierarchical information and performance information. Alongside of this, you want to know the polling interval that it's collecting at, because these are differential counters, so it's going to give you the average of that value or the sum, depending on the counter, on whatever polling interval you're collecting it at. Pretty basic stuff, plus a server name, because we kind of want to know what we're collecting it from. Let's go to a relational model. How many of you are actually doing this sort of thing today? This is perfmon information in a relational database. And it queries just fine. In fact, we have actually been doing something similar for a long time. We've got it up on Azure SQL DB. We collect perfmon information from a lot of folks, import it into a database, and run a bunch of analysis on it. No big deal. It's a very straightforward relational model, but essentially it's 5 tables, one for each one of those hierarchical layers. Okay, well, any single time that you want to go query on any of this stuff, you're looking at a minimum of 4 table joins. It gets to be a little expensive. Now, we're pretty used to this stuff. This is what we do, right? But now, collect perfmon information from SQL servers all over the planet. And these are some of the things that we do. We've got customers East Coast, West Coast, a couple in Canada, one in Germany. And we want to go collect this information long term so we can do baselines, capacity projection, things like that. So, if we've got our data center up, let's say in Azure East, well, if we've got metrics coming from it all over the place, I'm sorry, but it's like we love infrastructure, but we can't beat physics. It'd be really cool if we could, man. We'd all have some new toys if that could happen. But we got to collect this information, and the round-trip latency from places like New Zealand or Japan or Europe, it's not like we're talking about 1 or 2 milliseconds like you're in your own data center. I mean, we're talking hundreds of milliseconds to get around the globe. Even if it's locally, the round trip can be 50 to 100 milliseconds even in the continental US. That's kind of a challenge, because if we're querying this stuff, every single round trip can go take this long. Now, for a lot of perfmon data, it's not a huge deal for this unless you actually want to start alerting or trending or this kind of thing, and you got chatty apps, and the user experience just becomes poorer the farther away from these things that you get. And now build out the SQL server to go handle the sheer volume of writes from, let's say, 10,000 servers every 30 seconds. I can build stuff for reads, but writes are going to inherently block, and it's just tough. So now we got to deal with performance. So all flash, lots of RAM, big iron, plus an availability group for HA. So now we've got 2 of those, and then we got to handle DR. So now we've got 3 or 4 of these things. The cost behind this, just simply to collect the information, let alone do the analysis, is going to really climb quickly. And we're a small shop. We spent a lot of time over the last couple of years evaluating, is this the best fit for the technology? Especially given now we need actual HA. So let's say we want to try to get this stuff closer to the customer. Okay, so turn around. What's right? If I want to go build this out, I'm looking at each one of those SQL Server silos all around the world. So you're probably looking at about 100, 150K per site. And now we got to deal with transactional replication to get the data all over the place. That gets really expensive, it gets really complicated, and we can do this. And I'm sure we're doing this in a lot of different places for any of your environments. For this particular workload, is that the best fit? Probably not in this case. What if we can use something else that Microsoft recently started shipping, and we can actually say, yeah, give me an endpoint, East Coast, West Coast, Central, a couple in Europe, 1 in South America, 1 in Japan. And now the data is going to find the local or the closest node, and then it's going to start replicating behind the scenes with some eventual consistency. I don't need this stuff real time. I need it near real time. This could actually be a better model. It's pretty cool. So now, what do we have? We've got a data model. We've got a relational model. How can we actually turn around and turn this into something where we can actually use this on Cosmos? Now, everybody starts arguing, no, SQL, we don't have any consistency. We don't have any integrity checks or foreign keys or anything. You kind of do, but you have to go build it into it, kind of like with SQL Server. We just do it at a different layer now. The data model behind perfmon is nice and straightforward. Here's a payload, server name. We have a C# list of perfmon sets, basically, and then a document type. I'll talk more about that pretty soon. Each one of the sets has a name, and this would be processor, physical disk, memory, that sort of thing. And then a list of the counters for that set. Same hierarchy that we described earlier. Perfmon counter, counter name, a list of the instances. For each instance, now we have the instance name, now we've actually got our perfmon value, and now we've got our collection date and time, and we're going to do it in UTC because you should all be collecting dates and times in UTC, right? Anybody here play with JSON on SQL Server 2017? Isn't it kind of cool? When it's the right use case. What we've got now is essentially a JSON payload that represents our perfmon data. And you can see here, server names, set names, counter instances. And I'll go through a big demo here towards the end, and we'll talk through a lot of this stuff. But this is more of what we're representing now. And now we can transform it, we can query against it, we can do whatever we need with this stuff. So, okay, so that's a high-level overview of where we're going to go with this. So now, what the heck is it?
All right. So Microsoft's definition of Cosmos DB, if you haven't seen it already, is that it is a globally distributed, massively scale, multi-model database service. So what exactly does that mean? Let's kind of break that apart for a second here. So Cosmos DB is globally distributed. You'll see the map on the screen here. This is the Azure map of all the regions that are currently in existence. And in every dot, there is a Cosmos DB region as well. So Cosmos DB is literally anywhere that Azure is, and it will be going into the future as well. Any new Azure regions that pop up, Cosmos DB will be there. This will allow you to distribute your data anywhere that Azure is with really just about 3 clicks. So it handles the distribution itself, but it is everywhere. Similarly, it's massively scalable. You can take and scale up or down whenever you want. If you need more capacity and more speed because you're an e-commerce site and it's Black Friday, hit the plus button and purchase more throughput. You have it. You want to scale it down later because it's a time of lower activity, scale it down. You just save some money. It can scale up or down with essentially without limit. It's also very low latency and multi-model. So Cosmos DB supports 4 different models currently. There's a key value model, column family. There's the document model, which is what our demos today will be based on. And if you have graph data, it can handle that model as well. On top of that, it also has multiple APIs. So it currently has 5 APIs. There's a table API, MongoDB and Cassandra. So if you have an application that is currently working with MongoDB and Cassandra, you can use the Cosmos DB, MongoDB, or Cassandra APIs, point the applications, add it, and it will act no differently. There's a Gremlin API if you're doing graph data, and then we have the actual SQL API. And the guidance I've received on this is that if you're doing net new development in Cosmos DB, start with the SQL API. There's also 3 more APIs at the bottom there you can see that will be coming soon. So there's clearly more work going on in this space. What I like to define Cosmos DB as is it's a database service that's featuring an engine that can excel at several things, but what really makes it special is its ability to do partitioning and replication and geoscaling. And as David has pointed out a couple times now, this is a NoSQL database, right? There is no relational model in Cosmos DB currently. I don't know if one will ever be there. It seems extensible to the point where that might be a possibility in the future, and I have no insider knowledge or anything, but currently it is not a relational database. It has non-relational models only. So a brief history of Cosmos DB. Microsoft started having internal problems with scale in their apps, and Microsoft was really smart and realized that if, hey, we're having this problem right now, our customers are probably going to start having this problem in the not-so-distant future. So in 2010, they started off, and they called it Project Florence, and started figuring out how they were going to deal with this. And in 2014, they released the first iteration of that, which was called Azure Document DB. Has anyone here worked with Azure Document DB at all? Okay. Couple hands. So that was the original release, and then in 2017 it was rebranded and expanded and released as Azure Cosmos DB instead. Microsoft uses this internally all over the place. I like to use Azure Active Directory as a great example. That's in Cosmos DB. If you're a gamer in Xbox, the features to allow game playing across multiple machines across the world, that's all handled. Additionally, Office and Skype and plenty of other places are all leveraging Cosmos DB internally. Cosmos DB is, in fact, designed for the cloud from the ground up. It's a cloud product. There was never any intention of making it an on-premise solution. It is a cloud product through and through. So what does Cosmos DB offer us? Number one is fast data distribution. I talked about how it is a foundational Azure service, which means it is present in every Azure region and will be going forward. And this enables you to put your data wherever the users are. Wherever there's an Azure region nearby, you have Cosmos DB, and users can potentially connect to that region. Cosmos DB has what's called a multi-homing API, which means you have a single endpoint you connect to, and it will automatically determine where the data resides that you need to get to and what is the closest region that will give you the best performance to get to it. So you don't have to worry about connecting to this region versus that region. You just connect to one API and it handles the rest. All the replication between whatever regions you select is automatic. It happens in the background. For you, it's easy as just saying, I want my data here, and go and click. And it will take a little while to replicate the data to that locations, but there is 0 code changes to your code to deploy or remove a region from your Cosmos DB. It handles both manual and automatic failovers. You can add or remove or have it fail over as necessary. And it really is designed from the ground up for HA. We talked a little bit about scale, but the beauty of Cosmos DB is that both your storage and your throughput can scale transparency. You essentially have a plus or minus button, and if you want faster, click plus, right, and pull out your credit card. But a single machine will never be a bottleneck with Cosmos DB, frankly, because you'll never have a single machine with Cosmos DB. You have lots and lots of infrastructure behind the scenes at different layers making this happen, and we have a graphic in a little bit that kind of dives into that a little bit. And your collections in Cosmos DB can scale from gigabytes to petabytes across, as many machines and regions as you want. You also get guaranteed low latency. So your requests, as I said, due to the multi-homing API, will be served from the nearest region, which is awesome. It is a write-optimized database engine, which is latch-free. So there is no locking because there's no locks, period. I like to kind of compare it to SQL Server in-memory OLTP. It is not the in-memory OLTP engine from SQL Server, but it is a latch-free engine like that one.
This is one of those areas that is really critical here, because if you've ever dealt with IoT or massive metric collection from a whole bunch of machines, or just trying to pull in data from tons of places, writes are one of those things with SQL Server that we have to engineer very carefully. We can scale out reads pretty easily, but writes right now are pretty centralized, and we've got to deal with locking and blocking on these portions of the databases that really deal with this. Now, big deal. We can just make this work, turn it on, scale it out. Life is good.
Absolutely. So indexing in Cosmos DB is synchronous and automatic, happens in the background. By default, we'll talk about how indexing works, but by default, everything you put in Cosmos DB is indexed. You can absolutely change that if you like, but right out of the box, if you do nothing, that's what it will do for you. And they guarantee, due to all this, they guarantee single-digit millisecond latency at the 99th percentile. So if you're doing a 1 kilobyte read, 50th percentile will be less than 2 milliseconds to get that data back, and at the 99th percentile will be less than 10 milliseconds. Writes are less than 6 and less than 15 for a 1 kilobyte write. So they are guaranteeing you, they're giving you an SLA of this level of performance. Similarly, Microsoft will give you a guaranteed SLA in terms of availability. You get 4 nines of availability if your Cosmos DB exists in a single region, and if you have multiple regions, you actually get an extra 9 on top of that. You get 5 nines. And as I said before, it is a highly redundant architecture that can handle all this, and failover is automatic or manual, as you prefer. All right, so how does Cosmos DB work?
Magic.
Yeah, exactly, right? It's a giant magic box. So let's talk about SQL Server's resource model. Hopefully we're all familiar with this, but SQL Server kind of has 4 tiers in its resource model, right? We have a server. The server can hold 1 or more instances of SQL Server, which can contain, each instance can contain 1 or more databases, and databases contain lots of objects, right? It's tables, views, stored procedures, triggers, functions, you name it. That's, the SQL Server hierarchy we know and love. Cosmos DB also has a 4-tiered resource model, but it's different. So there's an account, which can contain 1 or more databases. And here terms get a little more generic. Databases contain containers, and this depends on what model you're using, right? So if you have a document model, well, your container is a collection of documents. If you have a graph model, well, your container is a bunch of nodes and lines and stuff. So it's kind of abstracted, and then similarly below the container level, containers contain many different types of items, which again depend on your model. So at the container level itself, this is where the actual data model matters, right? So as I said, if you have a document container, well, then you get a collection. You can have a graph or sets of key values or column values. Also, what happens at the container level is the throughput, right? The scale level of this. You can choose whether or not how many request units you're going to use, which are kind of the currency of Cosmos DB in terms of throughput, and we'll discuss that in a little more detail in a second. But that all happens at the container level. So you have a database with multiple containers, which each could have their own throughput settings. Oh, and here is a screen right now, actually. So when we add a collection, we choose which database it goes in, give it an ID, and then, as you can see at the bottom there, we would actually choose what the throughput is going to be if this pointer is working.
Define the partition key now.
Yes, that is very important. And if you were in our session yesterday, we spent a lot of time talking about partitioning and partition keys, but this is particularly important. When you define a collection in Cosmos DB, if you are using the unlimited storage capacity model, right? You get two here, you get two options. You get a fixed, which is 10 gigabytes, and an unlimited, which is unlimited. The fixed 10 gigabyte capacity essentially means you get one physical Cosmos DB partition. So you would not have to provide a partition key because we're essentially not doing partitioning. One of the hard limits in Cosmos DB is you get 10 gigabytes of data per partition key. So by choosing a fixed size and only one partition, you're then limited to 10 gigabytes. If you want more than 10 gigabytes, which I imagine you would, select unlimited, but then at that point you must provide a partition key, and that cannot be changed without deleting and recreating the collection. So that's something you gotta think about ahead of time. All right, and then below the container level, again, the types of items we have depend on your data model. They could be documents or nodes or edges or rows and items. But also, Cosmos DB provides stored procedures, triggers, and user-defined functions. These are all items that exist within containers. Question?
Just to differentiate, because we hear this word all over the place right now, this Cosmos container is a completely different functionality from a Docker container. Is that correct?
The question is, go ahead. So the question is a Cosmos DB container completely different from a Docker container? And that is absolutely correct. There is just the same word being used, but they are completely different constructs. So,
Yeah, no, it's buzzword bingo with a lot of this stuff.
yeah. So Microsoft provided this excellent graphic of the system architecture of Cosmos DB, and there's no way I could recreate this on my own. So we're borrowing their image and attributing it to them. But they essentially show here the Earth has multiple Azure regions which contain one or more data centers. Data centers are built on stamps and fault domains and have multiple clusters. Clusters contain machines which contain containers. Containers have replicas within them, et cetera, et cetera. There's a whole bunch of different layers in play, and this is why you'll never have a single machine failure taking down Cosmos DB.
Yeah,
There's so many layers of redundancy built in.
I'm glad they started with Planet Earth because we have more than one of those to differentiate between.
Maybe that's a single point of failure. Okay, so request units. This is, as I said, these are kind of the rate-based currency of Cosmos DB, and they represent a combination of CPU, memory, and I/O. So it's kind of like a DTU if you've done work in Azure SQL database. One request unit is designed to be a read of 1 kilobyte, and literally.
Yeah, and the CPU and the memory associated with the read action.
And literally everything you do in Cosmos DB has a cost assigned to it in terms of request units. So whether you're writing to the database or reading from it, or it's doing maintenance on its own in the background, or executing a stored procedure, whatever you have, everything literally has a request in terms of or a price in terms of request units. And you see, it will tell you that here in the Data Explorer. You can actually pull up when you run a query. It'll tell you how many request units this particular operation cost. Now, you provision request units in terms of request units per second. That's the fast button, essentially, is how many request units per second do you want. And you essentially get a allowance of request units, if you will. Except this isn't an allowance you can save up. This is a use it or lose it this second type of allowance. So if you purchase 100 request units per second, hi, I have 100 request units. If I don't use them, well, I get another 100 the next second, but the 100 I bought, I don't get to save or anyway. Everything you do deducts from that allowance until you get another allowance the next second later. You can change your request unit limit at any time, right? You can provision more or less as you want, and it will take effect literally instantly. If you exceed your request unit budget, this is when you start getting rate limited. So your performance might go down. Go ahead.
The good thing here is that it's not like it's going to just kick back your request and say, yeah, you've exceeded your limit, go away. What it does is the API is actually smart enough to say, if you are hitting this rate limit, you're banging off the ceiling there, it basically just pauses and retries until you get more RUs to go work with, and then over time, it fulfills your request and then ships back the payload. So it is pretty handy like that.
It's nice. And if you don't like the fact that things are taking so long, well, then you can click the plus button and purchase more request units and get more throughput. That's simple. It's a direct financial incentive to have good performing queries, essentially, right? You can pay for poor performing queries literally in terms of money and figuratively in terms of performance. If you are not using all of your request units, you have some period of relative inactivity in your system, well, this is when Cosmos DB will go ahead and run its background tasks, which also have a cost in terms of request units, but it will try not to run them until there's spare request units available. So it does internal index maintenance. It also has TTL expiration, so you can define, how old a record should be in Cosmos DB, and once it expires due to this time, it can do something with it. It can move it somewhere else. It can delete it, et cetera. I'm sorry, could you repeat the question?
Oh, TTL.
TTL, time to live.
Yeah. Question is, what is TTL?
Yeah, sorry.
Time to live on the request itself.
Correct. All right.
So the question is it automatable, the act of increasing or decreasing the RU allocation? They don't have a direct front-end way to do it, but it can all be done with PowerShell, and you can just say R, and it actually keeps track. Where are you hitting your rate limit in there? And you could actually programmatically detect that and bump it up and down if needed, as long as you set a ceiling on that to be smart so you don't crush your credit card.
Cool. All right, so the next kind of foundational thing we'll talk about here briefly in Cosmos DB is, in fact, partitioning, which is really important. In fact, it's the most important thing you can do in Cosmos DB. So partitioning in SQL Server is very, very physical, right? We define a boundary between partitions. We create a partition function in SQL Server. We say partition function as left and a couple values, right? Like maybe left 100, 1000, which would create 3 partitions because we created 2 boundaries. We create this partition function, and then we create a partition scheme which maps this partition to a physical location, to a file group, right? So we can have multiple partitions pointing to the same file group, or we can have, every partition gets its own file group. The way what happens then is, you end up, because we've created boundaries, we have similar values within the same partition, right? That they're all within the boundary, they're relatively similar values. And this can really lead to a hot partition, especially if you're partitioning on dates, which is what people tend to do, right? So if I have a table that's partitioned on dates, well, I'm probably going to insert a lot of data from today, so the current partition is most likely to be hot, whereas I'm probably not changing values from yesterday or, a year ago nearly as often. But partition management in SQL Server is very manual, right? We have to create new partitions, adjust the partition functions and schemes as necessary. Maybe we have an automated process to do this for us, but we had to manually write this process to make it happen. You also have a hard limit in SQL Server of 15,000 partitions per table, which has been the same since, I believe, SQL Server 2008 R2. It was previously 10,000. I think they upped it to 15 at that point. But we have a limit of the amount of partitions, and partitioning is based on value ranges and is extremely physical. Cosmos DB has very little in common with this. So there is no partition range because every partition key is hashed. So as soon as we do that, things become quite random, right? That's the whole idea of hashing, is we take a value and make a similar, a relatively pseudo-random value out of it thanks to the hash. But everything is stored together based on the hashes. So what this means is you really won't have a hot point because everything can go completely different locations based on this hash value. The hash of the number 2 and the number 3 produce wildly different values. There are logical partitions, which are the keys themselves, and they are spread across physical partitions, which are managed by Cosmos DB, and we have a graphic that will show this. But partition management in Cosmos DB is completely automatic, so you are not creating partitions. You do not tell Cosmos DB, I want this data to be across 8 partitions. It handles all of that for you. If it needs to split a partition, it will handle that automatically for you too. This just occurs in the background. And there is no limit on the number of partitions in Cosmos DB. So in SQL Server we had 15,000. Here it is unlimited. But the one limit you do have is there is a 10 gigabyte maximum of data per partition key. So if you have a situation where you have more than 10 gigabytes of data for a given partition key, you chose a poor partition key. You should always in Cosmos DB err on the side of having lots and lots of partition keys. That actually will give you better scalability than just having a few. How do I, what was the question?
That is, in SQL Server, you have your fields and columns, and you made the association in the function. How do you do the same in this?
So the question is, how do you determine what the partition key is in Cosmos DB?
What is that is, or by now I don't understand what is a partition.
Tell you what, let's get to the demo here shortly, and I'll actually show you some examples of this. It'll become a little bit more clear there.
The question was, how does the hash function deal with collation? How do you deal with hash collisions? Is that, okay. They produce the same hash value at that point. So that would be, one of many ways. As I said, everything in Cosmos DB, the actual values are indexed as well. So if you are, if I am saying, fetch me a value where, and I specify the partition key value and it goes to a hash, and there's another value that somehow has that same hash value, hopefully not likely, at that point it would know which partition to go to, but it would then be able to scan and find the value I requested as opposed to the other value which had an equivalent hash. But moving on, the most important, as I said, design decision you can make in Cosmos DB is your partition key, essentially. It has a real dramatic effect on efficiency of query execution, where they get routed, and request and storage distributions as well. So this is something you really want to think through and test in your design phase, right? Just like if you have a SQL Server database and your table schema is poor and you have to redesign that later, that can be a very painful process once something has gone live. This is the same way in Cosmos DB. This is one of the things you really want to think ahead and evaluate ahead of time. So I showed this screen already, but this is essentially where you choose your partition key. As I said, you get a choice of one fixed 10 gigabyte, which is essentially one partition, at which point the partition key screen goes away, or unlimited, and you must put a partition key in at that point, and there is no opportunity to change the partition key once the collection is created.
So let's go a little more real world on this one, and this will help answer your question, sir. Step back from the technology for a second. What data are we actually collecting? In this case, we're collecting perfmon information. So we know we're going to be collecting the server name or some identifier for a server. We know we're going to have the counter set name. We know we're going to have the counter name. We know we're going to have the instance name. And then we've got the actual metric that we're looking to collect. And then we have a collection date and time in some date and time format that's really precise. Okay. We know that's what we're working with. Now, how are you going to be accessing the data? We're going to be storing a lot of this stuff for a lot of different servers for a long stretch of time. Are you just going to query by a server name? Probably not. It represents a lot of bad third-party code that we've seen. I'm going to query and get 50 gigs of data back, and then I'm going to look for one record. Really inefficient, very expensive. So we're probably not going to do that. But we're going to use a server name as a filter behind it. Date range. Am I looking for alerting for things that are going wrong today? Possibly. Am I going to be looking over trends from the last week? Most likely. And am I going to be comparing these day after day, going backwards in time? You should be. So now we've got a server name, date range. But I don't just need that. I may be interested in these very specific counters. If I've got something that's shooting up the CPU every night at 11 p.m., I'm going to want to filter by certain counter and counter instances. So now, this is how we're going to be querying this stuff routinely. So server name, date range, and probably on a specific counter. So in this particular data set, that's what we're going to start using to design our partition key. Okay, so if we just partition by server name, well, your storage distribution could be higher or lower depending on different things. Like, a 2-CPU machine is going to have less performance data than a machine with 144. So our distribution will be similar. It'll be linear based on those different metrics, number of network adapters, number of hard drives, things like that. So your distribution, fairly predictable based on the scale of the machine. But if you go just by server name, remember that 10 gig limit, you will hit that cap at some point. So we got to go a little bit further. If we do the throughput distribution on this as well, our writes are going to be very similar across all the machines on whatever time you're collecting and doing the insert. So that's an even distribution there. Our reads are going to be on really hotspots on whatever you're actually querying and scanning against. So you'll see hotspots just jump around as people are using this. So probably not the most even there. Okay, let's do it by collection date. Okay, well, storage distribution by day should be very similar unless you add a new machine in there. Okay, no big deal. Nice and straightforward. Our throughput distribution, just about everything that's not today is going to be super idle, if not even read-only from a write perspective. From reads, it all depends on how you're using it. Chances are, though, we're reading back the data that we're inserting today to look for things like monitoring, stuff to alert on, things like that. So today's partition would be very hot. But then we still have to filter by server and counter and things like that. What if we did a composite key? Now keep in mind, the key value is completely up to you. So you can be as granular as you want with this. And again, err on the side of caution based on your data set. So what if we did server name dash year, month, day? Or day of year, or day of year plus hour of day. Something like that. Something in order to start slicing and dicing this. So if you start looking at a composite key on here, your storage distribution will be fairly similar. It'll be almost identical unless you're adding machines or changing counters. Your write distribution is going to be spread out based on machine plus the date stamp, or however you want to do it. Our reads are going to be scattered all over the place, which means the distribution is going to be actually very advantageous from a query lookup, because if I'm querying things, you're going to be doing a date filter on it, and it's going to be able to seek very quickly to that record and keep the RU charge very low. This is going to help you scale this better. But again, this is completely up to your workload. Yes, sir? Question is there a maximum length of the partition key? That is a good question. I know it's very long. I don't know the specific value, but grab a card, send me an email. I'll find it. Granularity. We've talked about this. Too granular, one record per partition is probably going to be pretty expensive and just go berserk. I know this because I tested it, and Cosmos DB did great. It just took a little bit longer to find stuff because I like breaking stuff. What can I say? Bottom line, it's your data. You know the data that you want to put in here. I mean, telemetry data, logging data, things like that. Experiment with a proof of concept. Worst case scenario, tear the collection down, create a new one with a different partition key strategy, and rebuild. You can move data, but it's up to you to write a program that essentially extracts the data from the old container, transforms it, and reinserts it into the new one. It's not like you can actually query cross-container here, and that's a challenge. Now, and we've stressed this 1,000 different times, this really is the single biggest decision point you have going into a Cosmos DB strategy. Have to go do this. Err on the side of more partitions. Worst thing that happens is you have a little bit more to accommodate. For example, if you're going in and scanning the individual perfmon values, when do you know where you started collecting data? So in addition to storing the data, you may actually want to store in a different document the actual days that you are collecting perfmon data. And that way you can fetch that and look at a start date, end date, individual days you collected, and then go query on the individual day. Yes, sir? So the question is, in SQL Server, you only have one column that you can really choose as a partition key. In this case, it's one field, but it can be whatever you want. So if you used a column and some delimiter and a different column, essentially, and a different delimiter, et cetera, you can go as long as you need. So the question is there a way to basically purge out old data routinely? It would be easy to write something to do that as part of a scheduled task.
TTL expiration as well.
What was it?
The TTL expiration.
Oh, there's also TTL expiration in there, so
would
you
do
could
that.
actually automatically do it. I haven't played with that personally, but we can. Yeah. Okay, consistency. Again, this is the second biggest decision point you need to make with this.
So we have multiple replicas in a Cosmos DB deployment, and they're potentially very far apart, right? This is great for high availability. We have copies in very different locations, provides us a good level of protection there from disaster, hopefully. It also gives us great speed, right? Because it's more local to people in different places. They can connect to the closest and get better speed. That's kind of why we're replicating, so that we can achieve this high availability and this better performance for users. But with it, we have some interesting challenges in terms of consistency. So we're going to go back to our graph here of the overall topology of Cosmos DB, and we're going to focus in on the part that's highlighted in yellow here, the replica. So Cosmos DB has a unit that is called a replica set, and we've kind of illustrated it here. It contains 4 replicas of the data. So there is a leader replica, which is where changes would propagate in from, whether you're modifying it yourself or if the changes are propagating from another replica. The changes are also stored in 2 followers within the replica set, and there's a forwarder. So if there's multiple replica sets for multiple regions, this is how they would communicate. You'd essentially have like this. So let's say we had a Cosmos DB deployment in 3 different locations. We have Central US, UK South, and Japan East. The changes that occur in North Central US will get propagated from its forwarder to the leader and receiver on UK South and Japan East. So Cosmos DB has 5 different consistency models to manage how consistent the view of the data is. This is kind of akin to SQL Server's isolation level setting, right? SQL Server has 6 different isolation levels, and I was actually talking about those here last year. Cosmos DB has 5 different consistency models, so you can choose what gets prioritized in terms of consistency when you are reading from different replicas across the globe. You set a default at the database level in Cosmos DB, but then you also can override this on a per request basis. So this is very similar to SQL Server, where you can set an isolation level, but then within a transaction you can declare a different isolation level and make use of it. Do the exact same thing in Cosmos DB. So the 5 different consistency models Cosmos DB provides are there's strong, bounded staleness, session, consistent prefix, and eventual. So as we go, as you read from left to right, you have the most strict to the least strict. And this provides a really good spectrum of consistency depending on what the needs of your application are. So the most strict is strong, and actually strong gives you a linearizability guarantee. So any read with strong consistency will always return the most recent version of an item, and writes are only visible after they were committed by a quorum, right? Very strict. It used to be if you were using the strong consistency model, you were limited to a single Azure region. That is not the case anymore. You can use strong consistency across multiple regions, but if you are doing this, you do not get the performance SLAs. Because if I'm going to write a change here in Seattle and replicate it to Japan and have to wait for that to commit before it comes back to me, it's not going to perform very well, right? So you don't get the performance SLA if you're using a strong consistency model in multiple regions, but you get that SLA for every other consistency model. Strong is very strict. I would argue that if you are developing with Cosmos DB, you probably don't need the strong consistency model. I think some of the other 4s will give you exactly what you need. On the other side of the spectrum, we have the eventual consistency model, which, as a SQL DBA, that was always the butt of the jokes, right? Especially when non-relational databases started coming out, it's, oh, it's broken. Oh, it must be eventual consistency, right? Well, eventual consistency guarantees that absence of any further writes, these replicas will eventually converge, but that's about the only guarantee you get. You don't get a guarantee of order, which is kind of important. So if David makes an update and I'm looking at the results as they come across to another replica, he may update something and I'll see a value change, but the value that changes may be an older value than what he just updated with. There's zero guarantee in terms of order. You get the lowest latency with this setting, but you get out of order and literally no other guarantees. But it's fast, right?
Yeah. So, this is actually useful. If I'm taking log data from a bunch of different machines, for example, we've got this at a manufacturing plant right now. They've got data just logging information from all these machines. I'm not changing any of it. It'll get there eventually, and it gets there quick. I don't care if it's out of order, because it's all got a timestamp on it. In this case, boom, just send it in there. It's okay.
So there is a legitimate use case for eventual consistency, and that's why it's provided. And there's plenty of cases where it is perfectly acceptable. If we kind of ratchet back and get a little bit stricter, the next one we have is consistent prefix. And consistent prefix gives us the guarantee of order. Everything else is like eventual consistency, but you do have a guarantee that any changes that propagate will propagate in order now. The next one, the middle of the road, is called session consistency, and this is the default. So if you create Cosmos DB deployment and do nothing, it will be set up with session consistency. This has the notion of a client session, so there's actually a session key that gets passed back and forth between you and the server, and when you are sending a request, if you want to define your request as being part of a session, you attach a session key to it. You get very predictable consistency within that session in terms of monotonic reads and writes. So you get the guarantee that if you make a change within a session, you can see those changes instantly. Who here has updated something on a website, clicked save, it says it saved it, and then you refresh the page and it looks like your change hasn't occurred yet, right? That's poor consistency in this case. So if you're doing session consistency in Cosmos DB and they were actually using the session correctly, then you would see your change instantly. Nobody else might. They have to wait a little longer, but within your session, you get this very predictable performance, and everybody else gets good performance, just might be a little more delayed. So that's pretty nice. I think that's an excellent default. And then if we want to get a little more strict than session, but not as crazy as strong, we have what's called bounded staleness. And this is where you actually define a window of how late do you want a replica to be. So this can be in terms of the number of revisions or in terms of a period of time. So I could say maybe I don't want this replica to be more than 15 seconds behind, for example, and it would enforce that. If a replica gets too far behind, Cosmos DB will actually start to prioritize getting that replica up to speed above everything else. And this could include limiting changes until that replica is back and valid within the time window that you defined. So you can have some very strict setting if you want, but then you could potentially see a performance limitation as a result. Overall, session consistency has done me fine for everything I've done with Cosmos DB. So as I said, this is selected right in the Azure portal here. We have that box up at the top where you actually select for a database what consistency model you want. And it has this really neat animation actually for each of the different consistency models with musical notes appearing on a staff and what it looks like from the terms of the writer, a reader in the same region, and then readers in different regions as well. So it's a tremendous little illustration of how that works. And a good question I've gotten before is, what if you're not doing georeplication? Does this matter? And in fact, yes, it does, because even if you only have a single region, you still have 4 replicas of your database within a replica set. So these settings govern within an individual region in a replica set as well. All right. Backups, right? We're DBAs, we love backups, right? Very, very important, obviously. And Cosmos DB has lots of redundancy built in, so hopefully we'd never ever need to restore from a backup, right? That's the goal, but still good to know how exactly they work. And they're actually pretty simple. Backups are fully automated in Cosmos DB, and they're implemented as a snapshot, which is taken and then stored in Azure Blob Storage. And it actually writes to 2 different regions. It will write one copy to the local region so that you get good performance, and it'll write another copy to a different region so that you get extra high availability protection from disasters, essentially. So you get speed and you get safety. This is really good. This is kind of what you could hope for in terms of a cloud product, right? Backups are taken care of. I don't need to do anything. Yeah. Okay, that's great. Here's the downside. These backup snapshots are taken every 4 hours, and only the last 2 are retained. So if you actually go to the documentation, it'll say, if data is accidentally dropped or corrupted, contact Azure support within 8 hours, right? Groan. So yeah, don't do that. You can, in fact, maintain your own backups. There's a Cosmos DB data migration tool. You can export your data to JSON if you want to do that. If you're storing the hundreds of gigabytes and petabytes of data that you might want to use, I'm not sure that's a great option, but that is something you can do. You can also use Azure Data Factory and export it from there. I'm hoping that eventually, and again, I have no insider knowledge, but it seems to me like if they're writing these snapshots to Azure Blob Storage, well, then why can't I just provide my own Azure Blob Storage key and we write them to my account? And I can pay to maintain those as long as I want. I would like to see something like that in the future. Maybe it's in the pipeline, I'm not sure. And then if you delete a container or a database on purpose, they will actually retain these backups for 30 days. But this is not something you can restore yourself. You need to contact support and have them take care of this for you. Question?
Can you trigger the export to JSON from PowerShell so that you can theoretically automate that every so often more is happening?
Question is, can you trigger the export to JSON through PowerShell? I have not tried it, but I'm pretty confident you can. That'd be my thought. I can't see why you wouldn't be able to. Yeah. Question? If you apply the TTL to your database, does the snapshot include that? I am not sure. I don't think it would, though. That'd be my thought. I would assume if it's deleted, that's a legitimate operation at that point, right? Sure. The question is, how do multi-master writes affect backup? So Cosmos DB allows you now, they didn't when it first came out, but now you can write to any region. It used to be that you could only write to a master region, and the changes would propagate from there to everywhere else. Now you can write to anywhere. So how does this affect backups? Well, the backups are taken in each region. So each region is going to have essentially its own backup of what it has. So.
Yep. That's correct. Yeah, the backup might not be consistent between data centers there, depending on the consistency and the time to propagate.
Cool. Okay. So what's it cost, right? This is probably a question people have been thinking of for a while. You know, what does Cosmos DB cost? It's actually not that bad. So you pay for 3 different things in Cosmos DB. You pay for storage, and that's currently $0.25 per gigabyte per month here in the US. And you also pay for throughput, right? Your speed that I was talking about, your request units. It is 0.8 cents per 100 request units per hour, or 100 request units per second per hour. And then you'll also, if you're doing geo-replication between Azure regions, you will pay the data transfer rate, and that varies by region. North Central US is 8.7 cents per gigabyte. It was announced at Ignite this year that they now have Cosmos DB reserved capacity. So if you're using Cosmos DB a lot and you know you're going to be using it in the future, you can purchase a year or I believe 3 years at a time and achieve some cost savings by committing to a longer period of time. And as always, when I put numbers on a slide, check the Azure portal for the most current pricing information, because this was accurate the other day and I doubt it changed, but you just never know.
The question was, if you're doing just a lot of streaming and telemetry data but not reading a lot out of it, do they differentiate between reads and writes for the RU charge? It's bundled together, so basically it's just RUs. And I'll give you an example of this here shortly.
And then if you want to try playing with Cosmos DB for free, there is a desktop Cosmos DB emulator you can install. In fact, our demos are actually running on that. We are not using Cosmos DB because we don't like to depend on network connections at conferences. You never know what might go wrong. So you can download this and run it on your machine for free. And it behaves just like Cosmos DB. You do not get the geo-replication features, of course, but you can see exactly how it behaves and handles everything. If you want to play for free in the cloud, they now have a Cosmos DB 30-day trial. And you can renew this an unlimited amount of time. So basically create a 30-day trial, load some data, use it for 30 days. At the end of the trial, your data will be deleted, but then you can immediately create another 30-day trial and reload your data and work more. You can distribute your data in up to 3 regions with this free trial. And I think this is really, really nice that they're doing this. So we have information about that in the deck here as well.
Okay.
And with that, let's do some demos.
Yeah, let's get real world here. How many of you are genuinely excited about this? Fantastic. Well, as of 20 minutes ago, if you go to my home blog, davidklee.net, all the code I'm about to demo is now available for you to download and play with. Again, your mileage may vary. Please don't use this in production. Please don't copy it and call it yours, et cetera, et cetera. The lawyers make me do that. So let's actually take a look at some code. Okay. First of all, I have the Cosmos DB emulator loaded up on my local machine. I'm going to refresh that because you actually get an authentication token. It times out after a little bit. I have a URI right here. I have a primary key. Feel free to take photos and copy that because it's just local to my machine and you can't get in from there. If you go over here to Explorer, here's what we've got. You can see we've got the API, and I'll give it a second to load here. Come on. It'll be a short demo. Love demos, don't you? Let's try this again.
Refresh the entire page, maybe.
Okay, well, we'll kill that. What's that? There we go, finally turned off. To fire it up on your machine, we'll demonstrate restarting this thing. To fire it up on your machine, it's basically just that. It runs in the background over here. It takes a couple seconds to load, and then inside a web browser is how you go admin this thing. And honestly, it looks almost identical to what you see inside the Azure portal. So you can see I've got my database. I have my collection. I'll zoom in here. There's my collection. And essentially, nice and straightforward, I have documents. Right now, I don't have any. Let's put some in there in just a moment. Scale and settings. This is where you can actually go set the throughput. Now again, you get charged by RU. There are minimums depending on the scale that you need. In this case, because this is local, I got this thing set pretty high. The time to live value, right there. Right now I've got it turned off because I want this thing to persist. And then they've got some JSON down if you really want to go deal with a lot of the extra parameters and things you can to go turn this on. But right now, let's just focus in on the documents. So the thing that I have available for you all to download is a Visual Studio 2017 package. There are helper functions in here. There's some console arguments. There's this processing thing for multi-threading, pretty dull and boring. The interesting stuff that we've got is Cosmos Instance. This is a helper class. A lot of this stuff was pulled directly from MSDN, tweaked a little bit. Again, just play away. But what we've got here are helper functions where we can create a collection if it doesn't already exist. We can query a single document with an asynchronous task. I'll zoom in here so folks can see this. And again, it's a lot of nerdy technical stuff. This example is done in C#. If you know Visual Studio, you can kind of hack your way through a lot of this stuff. There are a lot of different APIs. There's also a REST API for a lot of this. It's very, very powerful, very extensible. So update doc, create doc, delete all partition documents, etc. Ignore this kind of stuff. We're just going to use it. So if we go over to perfmon, I've got counters. What this class does right here is this will actually give you the ability to define perfmon counters and the machine and actually go pull the data. And you can actually do this for remote machines as well. Right now we're just set up for localhost. So if I just go back to the program, you can see basic stuff. Now I'm not a good programmer. Feel free to go ahead and bash me publicly for that. I don't care. I admit it up front. We're going to collect perfmon data every 2 seconds on here so we can get something to play with. So you can see out of my app.config file right here, I've actually got a lot of the endpoints. So I've got the endpoint, I got the database name, the collection name, and my primary key. That's your authentication mechanism. So what you can see here is I go and establish a new Cosmos instance. And now this is my connection, essentially your SQL connection, but just for Cosmos. I'm defining a new machine, localhost right now. Again, this thing can fetch remotely. So we're going to get started. We're going to collect some perfmon information. So I'm going to jump over to command prompt, and we're going to say collect perfmon. Just right there. Now, our instinct as DBAs is to start treating this as if it were a relational database. So essentially, for every document we're inserting, this is now a counter set, a counter instance, a performance value, and a date and time stamp. So that's how we normally think as DBAs. It's row by agonizing row. So you can see for every perfmon counter that I've got established, it's collecting it from this machine, creating a document for that counter, and doing an insert. So I'm going to cancel out of that. Now, inside right here, Cosmos DB emulator, I'm going to zoom in some here. If you hit refresh on here, you can now see I've got documents. And you can see server name, group name, counter name, instance names. This is going to be percent processor time off CPU number 2. That one's running at 100% for some reason. Probably because I'm wiggling the mouse around because, well, Windows, right? And then the collection date. Very, very granular, and I care about this because if I'm doing differential counters where I want to get average or percentiles between timestamps, now I'm very precise with those. One big thing to think about here is I have this labeled as a document type. I can store multiple objects as documents in here, and they can coexist. It's the equivalent of different tables. So for me personally, how I like to use this, I have a doc type for every document that I insert, and that way I can filter. Is this a perfmon value? Is this an entry for a server? So I've got details on that. Or is this SQL Server telemetry at the instance level? Or is this database telemetry? And then I'll have a different field for the database name, things like that. It's extremely flexible, extremely customizable, and this is how you can start to decide what's actually present in this document for you to go use. And then I've got a GUID in here as an ID. If you don't specify one, it's going to create one for you. Kind of like SQL Server, I got a row ID as well. And then there's this really long key down here. I'll zoom out just a little bit so you can see it. This is actually how Cosmos knows how to go fetch and find this stuff internally. So we don't have to worry about that. It's this big, long, ugly thing. And I'm hoping they release some documentation on this at some point so we know what makes that up, because it's kind of cool if you're a nerd. That's fun. Okay. So now, what we just did, though, we treated this kind of like a table. So we got different counters. You can see CPU 3, CPU 0, CPU 1, et cetera, et cetera. Well, that kind of doesn't defeat the purpose, but it makes for more documents that we got to sift through. So what I'm going to do is I'm going to come back over here, and I am going to delete, if I could type, delete all. Simple and straightforward. Doink. What this is going to do is delete everything I just put in there. And we're done. So now I'm going to collect perfmon documents. And you notice what this thing is going to start outputting, level 1, level 2, level 3. This is the perfmon hierarchy that I showed you up front. So let's say a processor, and then percent kernel, or percent of privilege time, and then the counter instance, the CPU number, and then the value, date, timestamp, things like that. And you can see we've also got a little counter at the bottom. Transmit and insert took 15 milliseconds, 17 milliseconds. This is running on a laptop that I got from Best Buy, and it's still able to go do it that quick. Your mileage up in the cloud is going to be even better than this, as long as you've got the bandwidth and latency to go transmit the stuff to the nearest endpoint quickly. You can also start to measure the time it takes to process and do this stuff after it gets there. I'll show you an example of that. So if you look, I'm going to come back here and refresh, and now check this out. Let's see if I can make some more room on the screen here. I can't.
On the right side of that API window, you can click and shrink it down.
Yeah. There we go. So you can see server name, set names. This is your JSON. So set name, counter instances, metric value, CPU 2, CPU 3, collection date and time. One of the interesting things you'll notice about perfmon is that, check it out, this is a very granular date and timestamp. These are not identical values. This is why you actually want to collect the date and time per counter instead of collecting them way up front. So now if you want to be extremely precise with this, now you can. And then I start scrolling down. Let's go over there. So if you scroll down, now you can turn around and say, okay, well, counter instances, same kind of thing, blah, blah, blah. Processor, percent user time. Get to the bottom, doc type, perfmon. I've now got a single document that contains every perfmon value, and essentially by building this hierarchy, what did I just really do? I just normalized it. Now I can save space because you're paying by space. Yes, ma'am. Okay, question is, why is the date time different? Because I'm actually sampling this in UTC time instead of computer time. And that way I've got precision behind me because we just went through the daylight savings time shift, and that way it's specific when I know where it came from. Okay, so that's a document. Yes, sir. Sorry, 2 megabytes. What is the size limit of the document? 2 meg. And right now, I know for a fact this perfmon payload is well within that, but that's another design point you have to take into consideration there. It's a good question. Question is this the only API? No way. This is one of the 5 that we've got available. For this particular workload, I found that the document API works best. It could also do key value, but then we've got some other fields we'd have to go worry about, and it gets a little uglier. In this case, works better this way. Okay, so let's jump back to the code here. Now, if you notice, individual code, so collect perfmon doc. Okay, I want to go retrieve one of these things. So now I'm going to jump back here, and I'm going to grab an ID value out of there so I know exactly what I'm looking to go do. And in a single document query, you notice this is kind of like SQL, sort of. Select star from C, C meaning collection. You could call this select star from B or D or foo or hamburger, you know, whatever you would like. That's the collection. You can actually do joins to the same collection. You cannot query across collections. Just keep that in mind. And then basically select star where ID equals and server name equals. And again, my partition key in this example is just the server name. I'm actually not demoing a primary key with the composite key that I talked about earlier. So I accidentally or slightly intentionally set you up with a time bomb on this to force you to think about how you are going to be accessing this. Because if you were to just start collecting stuff, eventually you're going to hit the 10 gig limit per partition, and this thing will stop allowing you to insert. Okay, so I'm going to take that, and I'm going to build that. And there we go. So now, I'm going to do single dot query. And what's all this gibberish? Well, that is my JSON payload for that document, just not very pretty. But now you notice, check this out. Document query RU charge. Because the payload is greater than 1K, it now had to work a little bit harder to go do this, and I just got charged accordingly. But that's not bad. I mean, this is set up for, what is it, 100,000 RUs per second? That's 3.74 to be precise. If you write queries that span partitions inside the code, you have to go tell it this is a cross-partition query. But as such, you can actually go span partitions, but your RU charge is going to be a lot higher because now it's essentially having to scan a whole bunch of stuff. So keep that in mind. The code is in here for how to go get this. And check this out. I'm a geek with this stuff. I want to see exactly what's going on under the hood of it as much as I can. So now I can. Retrieve document count, document size, output document count, index utilization, 100%. If you're trying to do custom indexes in here, you can actually see the coverage for the individual thing. Query execution time, 430 microseconds. That's pretty darn cool, especially on a consumer grade laptop. Execution times, lookup times, run times, and again, the request charge. How cool is that? By the way, this is all programmably accessible. So if you want to turn around and fire off an asynchronous thread to start recording all of this in Cosmos DB for the queries that you're accessing in Cosmos DB, you can. And if you wanted to, you could actually put this in a different container, shoot it off to the side, asynchronously collect it, and now you can start to analyze. What's my query? What's my request charge? And you can start to get telemetry on how you're using this stuff. And the actual space to consume all this, really tiny. The overhead for the inserts, nice and low, piece of cake. Pretty cool. And if you look down here, the partitions that Bob talked about are right here. From a scheduling metric perspective, I've got end time, number of documents, scheduling metrics. There's my physical partition ID. Response time, run time, wait time, turnaround time for transmission, all kinds of really good telemetry. Pretty cool. Some of the stuff you have to do manually from SQL Server right now. They've already got it baked into it. If anybody from Microsoft is in the room, it'd be cool if you could add some of this to SQL Server. Okay, so that's an individual document lookup. Now, we're probably not just interested in one document if we're looking to go analyze a lot of this performance information in here. So in addition to the single doc, I can actually do a multi-document query. So in this case, I'm just going to grab everything. Now, I'm going to jump down to the code on this one. You can see what I've done here. Let's say the select single doc. Select star from C where ID equals and server name equals. Now, it gets a little technical with the code, but the Newtonsoft JSON libraries will actually give you the ability to take the return value and give it a document. Life is good. Now, the constraints that we were all talking about, all these different things, this is where it gets a little more fun. We can actually enforce constraints, data types, all this stuff to get away from some of the stigma of NoSQL. We can now fully architect and design and actually control the data that's flowing in and out. Right here, I converted this to that object that I showed you. Here's a perfmon sample, json.convert, deserialize, cast it as a perfmon sample object. One line of code, and I've now got a strongly typed object that I can go use. If the field doesn't exist in the JSON, it's going to put it in there as part of the type conversion. The multi-document query, nice and straightforward, same exact thing. I've got something in here that says query based on the query, return it as a list of documents. I'm going to create a new return value there of the type that I want. For every doc in the return value, do the conversion, do the return. Nice and straightforward. It's not the easiest if you've never done this kind of stuff before, but it's good stuff that you could follow to do what you want. Now, let's go multi-doc query. And it runs, and yeah, that was nice and exciting. Ooh. Okay, so we got multiple sets of data now. This is stuff that you could pass into to the start of some analytics programs. But if you want to actually programmatically start to do stuff with this, well, I can turn around, and now I can do math. So based on the CPU counters, if I could type average val. If I wanted to say get the average of the total CPU counter for percent processor time for process, boom. Again, pretty dull. Average CPU utilization over the time sampled right there. I can turn around and actually do this. So the sample perfmon counter, it just loops. Pretty basic stuff. If you come over here, multi-doc average query. There we go. So essentially, same exact thing. I go get a payload of a list of those objects. Now for each one, convert it. This is the nasty code right there. But it turns around, and that's how we actually extract the value for that particular perfmon sample for that point in time. And now I can turn around and do averages. I can do min, average, max. I could do date range filters. I can do anything that I need here. And you can actually start to use this. It's a big shift from the database engine. A lot of times we use T-SQL to go do a lot of this stuff, and all the work is actually done on the database engine side. Now, it can be used really well and really effectively like this, or it can be misused. A lot of folks misuse this stuff, where they're trying to actually do true analytics inside the database engine, which is best suited for set retrieval, updates, things like that. This shifts that burden onto the application server, but this is how you do it. Cool. Got just a couple of minutes left here. And what I'm going to do is we'll do a thank you slide, and then we'll open this up to questions. So bottom line, I'm not telling you to use Cosmos DB for every single one of your workloads. It just doesn't work like that. What I am telling you is that you've got a fascinating and extremely advantageous new platform for certain workloads and certain use cases. And by playing with this stuff, download the code, tinker with it. It doesn't cost anything. You got the local emulator. Give it a try. And for some of these different workloads that you have, this might actually be a better fit for you. And who knows? Maybe this could be your receiver for a truckload of data, and then use SQL Server to actually pipe the data in to do what we're most comfortable with. But now you've got another tool in your toolbox, and now pick the best fit and start to explore. It's fascinating. It's powerful for when it's the right use case. So again, thank you all for coming. If you have any questions, please come on up here because they're kind of hard to hear from this big room. But again, thanks for coming, everybody.